Let's start. Hello, everyone. So we're going to continue talking about Markov decision process in this lecture, but we finally, are going to get into some real beef for this problem, and we are going to talk about how to compute the optimal policy for this lecture. Right. Just a quick announcement. So the Learning Strategy Center asked me to make this advertisement. So I think it's a great way for you to find study partners. As you know that for homework, we encourage you to work in teams and trying to learn from each other, right? So I think this Learning Strategy Center's tool might be useful for you to find study partners. Right. And before we jump into today's recap, I want to encourage you again to turn on your camera or video if you could, because it will be always nice to see your faces. And please keep asking questions during the lectures. Some of you are doing really well during the previous 3 lectures, but keep it up. And for those who haven't asked questions, I encourage you to ask questions during the lecture. It also helped me slow down the pace as well. All right, great. As usual, we're just going to do a 5 minutes recap about what we learned from the previous 3 lectures. Right, so we were mainly discussing the models itself. We were talking about this infinite horizon discounted MDPs, and we spent a lot of time talking about the Bellman optimality condition for value function. Right, so here I'm showing you a slightly different version of the one that we covered from the previous lecture. So here I'm showing you the Bellman optimality for the Q star function, right? So this is actually one of your homework 0 problems. So in homework 0, you will actually try to prove the Bellman optimality for Q star rather than V star. Right? Let me just quickly, explain the intuition behind this Bellman optimality. And in the homework, you're going to sort of prove them more rigorously. All right, so by definition, Q star SA basically means that you start from state S, you take an action A, then you follow optimal policy pi star all the way to the end, right? So we can just write this by definition. Right, so this means that I take action A at S, I get a 1-step immediate reward, and then afterwards, I'm just following policy pi from the next time step all the way to the end. Right, and so what is the definition of V star? So V star, we know that by Bellman optimality that we covered from the lecture, right? So this is max over A of R S prime, A prime, let me use A prime, plus gamma expectation as double prime. Right, and the term inside this max operator is essentially basically the Q star of S prime and A prime. Right, so this is just by definition of Q star and V star. Right, and if you recall that what we did for the value function version of Bellman optimality, we showed that for any value function V, if V satisfies the Bellman optimality, right, then this V will be exactly equal to V star. So you can actually show the same thing for Q version as well. So you will prove in the homework 0 that if you have a function Q, right, and this Q happens to satisfy the Bellman optimality condition, and then you can actually prove that for every state action pair, this Q will actually be equal to Q star. Okay, and in terms of algorithm that we covered from the previous lecture, we talked about this fixed point iteration, fixed point solution, right? So in high level, for 1D cases, this is the problem of finding, this X star, right? We know that X star is a fixed point solution of this function F. And what we proposed is actually do some very naive or natural algorithm, right? So this iterative fixed point solution algorithm, where you make a guess on the initial state, on the initial point, x0, and then you just iterate, right? And your hope is that, xt eventually converges to x star, right? Because we know that once you get to x star, this iterative process is not going to change, right? It's going to keep outputting X star. And what we proved from the last lecture is that if F is a contraction, right? In other words, if you look at two inputs and you map them to outputs using this function F, and you look at the difference between outputs and the difference between inputs, if the difference between outputs is actually strictly less than the difference between inputs, then this is a contraction map, right? So picture-wise, we have two inputs and we map them through function F, and we get two outputs, right? The difference between two outputs is actually strictly less than the difference between two inputs. And then we can show this iterative process actually makes sense, right? In other words, this iterative process generates the solution that actually gradually converge to X star. And then we use this intuition to do this policy evaluation, right? So what we can see from this Bellman equation is that this V pi, the policy's value function that we are interested into computing, is actually satisfy this equation, right? So you have V pi on the left-hand side, you have V pi on the right-hand side. And you can see that if I write this as this linear algebra fashion, right, this V pi, this vector, is actually a fixed point solution of this equation, right? And we can make some further abstraction. Let's just treat this R plus gamma PV pi as a function, a mapping that maps from a V pi to another V pi. Right? And then we can see that this V pi is actually a fixed point solution of this abstracted function. Right? So think about this T pi as some operator that maps from a vector to a vector. And then what we did is just do iteration. Right? We make a guess on V0, and then we just apply this linear operator T pi on Vt over and over again. And what we proved is that this operator T pi is indeed a contraction map. Right? And then, using the classic fixed point iteration analysis, we showed that this Vt converged to V pi exponentially fast. Right, so that's what we did, and this is basically the same sort of framework that we're going to use today as well. Right, so very similar idea. We define some fixed point equation, and we realize that the quantity that we want to estimate is the fixed point solution of the equation, right? And then we just make an initial guess, and we do this iterative process. And then in order to prove the convergence, we prove contraction first. And then this immediately gives us the convergence guarantee. Right, so any questions so far? Okay, great. So let's pose the question that we want to answer today, right? So this is probably one of the most fundamental questions that you can ask from Markov decision process. So if I give you a Markov decision process, right, the one that has infinite horizon and a discount factor gamma, right? So perhaps one of the most math fundamental questions that we could ask is that how we can compute the optimal policy pi star, right? We know that there exists a policy pi star that dominates every other policy everywhere. So how can we actually find it, right? So the reason that I add approximately here is that for this lecture, it turns out that we're also going to talk about an approximation algorithm, in a sense that the algorithm is going to keep outputting a policy every iteration. And we're going to show that when the number of iteration goes to infinity, that policy actually gradually converges to the optimal policy. All right, so motivations for finding the optimal policy. I mean, as I said, this is probably one of the most fundamental questions you could ask, right? So this is like shortest path finding algorithm. Like, give me a graph and tell me an algorithm that finds the shortest path, right? So this is kind of similar. Give me an Markov decision process. Give me an algorithm that actually outputs the optimal policy. from the A to the S many different policies. And in practice, because we can actually model so many things using Markov decision process. So if we have an algorithm that can actually find the optimal policy, then we can directly use it on all these applications, right? For instance, for Go, our goal is to actually find the strategy that has the highest probability of winning, right? So here, a strategy is a policy that maps from the board position, the state, to the action, which is the next movement that you could do based on the current board position, right? And of course, Go faces a completely different problem because the total number of board positions is larger than the total number of atoms in the universe. So computation-wise, this is very challenging, right? We cannot naively applying the algorithm that we're going to talk about today on the Go. And that's also one of the reasons why, we solved the other board games like chess 20 years ago, but we had to wait for another 20 years, for solving Go, right? And for robotics applications, for instance, for this manipulation problem, I want to find a strategy. So here, again, a strategy is a mapping, a policy that maps from the robot and board configuration to torques on the joints, right? So we want to find this strategy that picks the board and moves it to a goal position as soon as possible. Right, so the outline for today is that we're going to talk about an iterative algorithm. So this is an approximation algorithm. So the algorithm is called a value iteration. And you will see that this is a fixed point iteration algorithm again, right? And then we're going to talk about convergence, how fast they converge, for instance. And you will see that, we're going to do that via this very general framework, right? We're going to prove that this is a contraction. And then this immediately gives us the convergence. Right, very similar to the framework that we did from Tuesday's lecture. All right, any questions so far? All right, great. So let's look at some examples. So this is an example that we saw from probably last week, right? So we have this very simple 3-state to action Markov decision process. Right, so what we said is that we have reward everywhere, except that we have reward 1 in this particular edge, right? And if I show you this very simple Markov decision process, right, it probably took us 3 seconds to figure out what's the optimal policy, right? The optimal policy is a policy that maps every state to the action A0. But what about this Markov decision process, right? So this is still very simple Markov decision process that has 3 states and I believe 2 actions, A0 and A1. But now I make the situation a little bit more complicated, right? So in a sense that now if you look at state S0, right? And if you look at the action A0, if you take A0 at S0, it has half probability of going back to S0 and have half probability of going to S2, right? So now I'm showing you a stochastic Markov decision process in a sense that the transition to the next state is actually stochastic, is a distribution, right? And this immediately makes, the process of finding the optimal policy much harder, right? At least I couldn't really tell what is the optimal policy for this Markov decision process by just staring at this graph. So our goal is, let's design an algorithm that can actually automate this process of finding the optimal policy, right? So if I show you the reward, on all these edges, if I show you, this numbers, this scalars on these edges, right? So how can we actually design an algorithm that finds the optimal policy, right? So that now, whatever graph you give to me, you can give me a graph that contains thousands of edges and thousands of nodes, right? As long as you show me the cost, the reward on the edge, and these numbers, these probabilities on the edge, I can actually output an optimal policy. Right, so let's talk about a very naive algorithm, right? So this is gonna use what we covered from the Tuesday's lecture. So in the Tuesday's lecture, we know that we can actually do policy evaluation for any given policy type, right? We've already designed an algorithm that do that for us. It's an Like it's an algorithm that takes the reward function, the transition probability, right, and outputs a vector v pi that is very close to the ground truth that we want to estimate, right? And in fact, we first talked about an exact algorithm that actually uses a matrix inverse and computes the exact policy value function v pi. Right, so now we know how to do policy evaluation for every policy pi in the policy class. Right, so the naive algorithm is just do enumeration. Right, so let's write a for loop, right? For every policy pi in the a to the s many policies. So remember, we have a to the s many total policies, right? So let's write a for loop for every policy pi in that set. Let's just call this policy evaluation algorithm, right? So for now, for simplicity, let's just assume that we call the matrix inverse-based algorithm the exact policy evaluation algorithm, right? So once we complete this for loop, once we do policy evaluation for every policy in the policy set, which contains a to the s many different policies, right? Then we can actually just pick a policy pi prime such that it dominates any other policies at every state, right? That's by definition is the optimal policy. So that's the sort of the most naive algorithm that you could do by leveraging, the functionality that we built from the previous lectures, right? Now, the reason that I call this is naive approach because the computation-wise, this is terrible, right? If you record the computation complexity for this exact policy evaluation, right? So this takes us O of s cubic, right? And we have a for loop, and for this for loop, we have a to the s many iterations, right? So the total computation for this algorithm is actually as times s cubic, right? That's pretty bad, right? Especially, we definitely needed to get rid of the a to the s part, right? Because that actually gonna quickly forbid us to use this algorithm in real applications when s is like maybe 100, for instance, right? All right, so that will actually lead us to the approximation algorithm that we're going to talk about today. Okay, any questions so far? Okay, great. So let me define something called a Bellman operator, so which is a very classic quantity in RL. So given a function, a Q function Q that maps from state action pair to a scalar. So let me define a operator called T, right? So if I multiply T on the left-hand side of this function Q, I will get another function that maps from state action pair to real. All right, let's go slow here because if this is the first time that we saw this Bellman operator, right? So it might be a bit confusing. So all I'm saying is that we define an operator T, right? That we're always gonna left multiply this T on this function Q. And then the outcome of this multiplication is again actually a mapping that maps from state action pair to real. Right? And then let's look at the definition of this operator, right? So again, as I said, the outcome of this product TQ is again a mapping that maps from state action to a scalar, right? So let's just look at what's the output of this new objective measured at state S and action A. Right, so this is defined just to be the sum of the two usual quantities that we saw, right? A one-step immediate reward at state and action, and sort of the future outcome starting from the next time step, right? But here we are using the Q function here, right? So in other words, you can think about this T times Q as a black box, right? And it takes input SA and outputs a scalar. scalar, right? Which is nothing but just the usual quantity that we have seen many times. All right. Now we can actually, like what we did from the Tuesday's lecture, we can actually express this Q function again as a vector, right? A vector whose size now is S times A, because this Q is indexed by state action pair. So we have S times A many state action pairs, right? So we can express Q as a long vector whose size might be S, whose size is S times A, right? And every entry in that vector is the value measured at this particular state action pair. Right? So if we abstract this Q function as a vector, as a long vector whose dimension is SA, then we can think about this Bellman operator as a linear, not a linear operator, sorry, is an operator that actually maps from this RSA to RSA, right? Because the input Q is a vector and the output TQ is again a vector that lives in the space whose dimension is SA. Right? So basically we can think about T as a mapping that maps from the SA dimension space to SA dimension space. Right? So here I mentioned that this is nonlinear mapping. It's not super important at this moment, but this is actually different from the mapping that the linear algebra mapping that we defined for policy evaluation, right? So here, this mapping is actually nonlinear because of this max operator. Okay, so the max operator is a nonlinear mapping, right? So by nonlinear, I mean max over x of fx plus gx, right, is not necessarily equals to max of x plus max x gx, right? So this basically means it's nonlinear, right? So I apply the operator on the term f plus g, right? So this does not equals to if I apply this operator on f and g separately and then add them together, right? So that's all I mean. So this max operator is actually super weird. It makes things very challenging in RL actually. The reason is that this is nonlinear mapping. Okay. Any questions so far? So we're going to use this Bellman operator, right, for the purpose of making our algorithm, the fixed point iteration algorithm, look super simple, like it's a one-line algorithm again, right? But in your mind, you could always just zoom in into this like operator TQ and try to think about this TQ in this specific formulation, right? Which is the reward plus the outcome from the next time step. Right, so now we're going to design the algorithm. All right, so let's first convince ourselves that the thing that we want to compute. So we want to compute Q star. So this is our ground truth goal. Right, so let's convince ourselves that Q star is some fixed point solution of some equation. Okay, so record the Bellman optimality for Q star, right? So that's what we covered from the recap part of this lecture. So we have Q star on both sides, right? And the right-hand side is basically the Bellman operator that we talked about. So let me remind you the Bellman operator. This is TQ, right? Measured at state SA, right? So remember, TQ is a black box that takes state action as input and outputs a scalar R plus gamma expectation, Q V star S prime. All right, so now let's just abstract this equation from every state action pair to this big vector whose length is s times a, right? So we can actually write Q star in this very simple equation, right? So this Q star actually satisfies this particular equation. I have Q star on the left-hand side, and I have Q star on the right-hand side, right? So basically, we have already convinced ourselves that by Bellman optimality, right, and by writing things in terms of the vectors, we have convinced us that Q star is actually a fixed point solution of this very simple equation, right? I have Q star equals T times Q star. Right, so okay, so I actually want to stop here for a second, see if you have questions. Right, let me remind you again. So we are actually expressing Q as a vector. Okay, whose length is S times A, and every entry in that vector is the value measured at a particular state action pair. All right, so now we've already convinced ourselves that Q star is a fixed point solution of this equation. Right, so now someone want to give a quick guess about the algorithm that we're going to talk about. So in other words, can you design an algorithm based on the fact that we covered so far? Anyone want to give it a try?
I had a question. So for that equation to hold for it to be a fixed point solution, don't we have to prove first that it's a contraction mapping T, or?
No. Fixed point solution could satisfy, could be like, it could be a fixed point solution for any function. That does not have to be a contraction, right?
Okay.
Right. Contraction is used to prove the convergence. Like if your function happen to have nice property, then you converge, right? Otherwise, you cannot guarantee you converge.
Okay.
Right. So here I'm just showing you the fact, right? This Q star actually satisfies this equation, like, right, by Bellman optimality condition. But we haven't talked about algorithm yet. We haven't really touched anything on convergence yet.
Okay.
Right. Yep. Anyone want to guess the algorithm, or give a try on designing an algorithm for finding Q star?
Could you do something similar to what we did last time, where you set random values and then you iteratively apply the operator?
Yep, I think you're basically right. So this is basically the algorithm that you just described, right? So again, let's just do a guess, initial guess, Q0, right? So we're going to restrict Q0 to be inside this interval, 0 to 1 over 1 minus gamma. So this basically means that for all SA, so let's do Q0 SA belongs to 0 and 1 over 1 minus gamma, right? And let me remind you that this quantity is coming from the fact that 1 plus gamma squared all the way to the end is equals to 1 over 1 minus gamma, right? So basically the maximum possible reward that we could get is 1 over 1 minus gamma, right? So there's no reason for me to guess a point that is outside this region, right? Because I know that the quantity that I want to estimate lives inside this region, right? Okay, and then we just apply our Bellman operator on this QT, right? So the algorithm is super simple. It's again, a one-line algorithm. It's a two-line algorithm. And we can actually just prove that this process will converge by proving that this operator T is a contraction map. All right, so summary so far, we've talked about an algorithm, right? This is the algorithm that is very similar to the algorithm that we covered from the previous lecture, where we just do this iterative process. We do a guess on Q0, and we repeat repeatedly applying this operator t on the left-hand side of our estimator, right? So you can write one more step, t, q, t minus 1, right? And this is equal to like t, q, t minus 2, so on and so forth, right? So we just keep left multiply this operator t on our estimator, right? So, you might be not that comfortable about this operator for now because this is a very abstract operator that we defined, right? So one thing that we could always do is actually just zoom in into this like abstracted expression. Let's see, if we actually want to write a program, right? Actually, we want to write a program using some for loop, what we want to do, right? So let's just expand the definition of this Bellman operator again, right? So all we are doing is that at iteration t, right? I have qt available that is computed from maybe the end of the last iteration, right? So let's just do an update on the q value, right? All I'm doing is actually just compute the sum of this one-step immediate reward and the expected total discounted reward starting from the next time step, right? I compute the sum of these two values. I assign it to this particular state action pair and set it as the value of qt plus 1 at SA, right? And I'm doing this for all SA. So this is exactly what this abstracted quantity qt plus 1, this abstracted operation t times qt is doing. Right, so if you want to implement this algorithm, you can implement it in terms of this like a double for loop, right? The first for loop is the for loop for iteration. The second for loop is the for loop for all state action pair. Right, so we have a for loop here, and we have a for loop here, right? All right, so that's basically the end of the algorithm introduction. So you can guess, this is a approximate algorithm, right? Because we're using fixed point iteration again. So next, we're going to talk about the convergence of this algorithm, right? And then we're going to see how fast it converges. And we're going to do it again, via contraction argument. Right? Any questions so far? Okay, great. And as I mentioned, all we needed to do is just prove that this abstracted operator t, right, is a contraction map, meaning that I look at two inputs, q and q prime, and I apply t on them respectively, right? And then I calculate the difference between the two outputs, I compare it to the difference between two inputs, and I want to show that the difference between outputs is strictly less than the difference between the two inputs, right? So this is actually this quantity is talking about, right? So we want to show that we start from q and q prime, both of them are elements from this SA dimension space. And if we apply t on both of them, and our hope is that the difference between them measured in L infinity norm and the difference between the two inputs, again, measured in the L infinity norm, actually satisfies something that, expressed in this picture, right? The distance between two outputs actually gets smaller. And specifically, we will prove that it strictly decreases in a sense that there's a gamma factor that is strictly less than 1. Right, so this is very similar to the thing that we proved for policy evaluation. Right, so that's the goal. That's the goal we want to prove. Okay. And in high level, once we prove this thing, right, we can actually use the fixed point algorithm framework to prove the convergence. Right. Once we prove this lemma, the rest is very simple.
I have a question.
Yeah.
So in the previous lecture, we proved the contraction between Q and Q star, but here we are proving it between Q and any Q prime, right? Why are we doing that?
Yeah, so you're right. So for our analysis purpose, so first of all, yeah, so let me clarify your question. Someone actually asked me this at the end of last lecture as well. So in the previous lecture, so if you recall, when we do policy evaluation, we are proving a contraction between a vector v and the ground truth vector v pi, right? And we proved that if the contraction holds, then we can actually converge. But here we are actually doing something more general, right? We are basically saying that let's prove the contraction holds for every possible pair, Q and Q prime, not just like Q, Q star, right? So this is more general. Like if we can prove this, right, then we can definitely prove it's a contraction between a Q and a Q star.
That makes sense. Thanks.
Yeah. And for the previous lecture, you can actually prove that this policy evaluation step, this R plus gamma P, that operator, right, is also a contraction for any V prime pair. It's just that we didn't do that general analysis in the first lecture, right? But here I'm purposely, trying to state this lemma in a more general fashion. Like remember, recall this is for any QQ prime pair. Okay, so before we jump into the proof, let me quickly remind you the L infinity norm, right? So for a vector, the L infinity norm means that the maximum element, the maximum, absolute value among all the values inside this vector, right? Right, so let's just start by definition, right? So that's always what we do. Like we want to prove the difference between outputs is smaller than the difference between inputs. So let's just write out the difference between two outputs, TQ and TQ prime, right? And let's just arbitrarily pick a state action pair. All right, so the first step is just write out the expression for TQ and TQ prime, right? And remember that this is basically the usual quantity, right? A sum of one step immediate reward plus, the expected future outcome starting from the next time step, right? I'm just writing out the expression. I'm just zooming in into this T operator for both Q and Q prime in the first equation. Right, so we have Q here, Q pi here, right? And then now you probably can see what we can do next, right? So we have some nice thing. We can actually cancel this RSA immediately, right? And then we realize that, the expectation, the two expectations inside this absolute value, they are exactly the same, right? They are the transition from SA to S prime. So this expectation is the same, right? So then we can use the trick that we saw probably twice already, right? We can actually pull the expectation outside the absolute value. So that's what we did here. Okay, so now as you can see, the expectation is outside of this absolute value. Okay, so hopefully at this stage you've already convinced you that this inequality holds. Okay, and if not, you have a chance to just sit down and do the derivation in homework 0. Right, so again, all I did is just these two rewards cancel out, and I pull this common term, this gamma times expectation outside this absolute value, right? And the second trick is again the trick that you saw from maybe the second lecture or the first lecture, where I'm just pulling the max over A outside the expected value as well, right? So again, this is like the classic inequality, right? Max over x of x fx, max over x of gx is less than max over x gx. right? Definitely try to convince yourself this classic inequality is true, right? So it involves some sorts, like you need to discuss, cases by cases to prove that this is true, okay? All right, so the last step is something that we saw from the previous lecture as well, right? So here I'm just upper bounding the expectation by the max, right? So here I'm replacing expectation by max over S prime. So this is essentially saying some sort of average is less than max, right? So you can think about expectation as average, right? It's averaging based on some weights. So, it's some sort of average, average is definitely less than the max, right? Okay, so by definition, this is L infinity norm between the vector Q and Q prime, right? So now we're basically done here because we started by looking at the difference between the outputs, right, for every possible SA. And we proved that for every possible SA, the difference between the outputs is upper bounded by gamma times the worst possible difference between the inputs. Right? Write out one more step, just use the definition of L infinite norm. This is what we just proved, right? Remember, this starts for all SA, right? I've just proved that, for every state action pair, the difference between the two outputs is strictly upper bounded by this factor gamma times the L infinite norm between two inputs. Right, so this is a very simple proof, and it basically uses sort of the three inequalities that we saw before, right? Right. Yeah. So if you're haven't convinced yourself that these three inequalities are true, definitely spend some time trying to sit down and prove these inequalities. But I think the high level goal here is that we should try to understand this proof from a larger picture, right? So we want to prove convergence, and we have a nice tool to prove convergence, right? By first proving contraction. So that's all we were aiming to, right? So if you have this goal of proving contraction, then it's not super hard, for you to figure out these inequalities, right? Because you have some goals chasing, and you just need to figure out those like damn, linear algebra inequalities. All right, so the rest is actually very simple once we proved contraction, right? So we can just, starting from Qt plus 1, and we can actually compute the difference between Qt plus 1 and Q star, right? So just write out the definition of Qt plus 1, right? So Qt plus 1 is set to be equal to T times Qt, right? And then I apply this fixed point property. So this is from Bellman optimality, right? So remember, Q star is a fixed point of this equation. So I'm just using the Bellman optimality condition here, right? So now we have already proved the contraction for every possible Q and Q prime pair. And of course, this holds for this particular two pair, Qt and Q star, right? So now we get a sort of a one-step improvement, and we can repeat the same process over and over again, right? So if you do T many iterations, this is the conclusion that we're going to get, right? So the difference between our estimator Qt and the Q star shrinks exponentially fast, right? In terms of gamma to T. And when T approaches to infinite, we basically say that Qt approach to Q star, right? So this whole vector approach to Q star. In other words, Qt SA approach to Q star SA or SA. Okay, so that's what we proved. Right, so summary so far, we started from this fixed point iteration algorithm, right? So we call it a value iteration because every iteration we are computing some values, right? So this is a Q function. And then we basically use our usual machinery, right? We start by proving that this operator T is a contraction map, right? And then once we prove that, the rest is very straightforward. We just prove that, this converges exponentially fast. And the difference between Qt and Q star shrinks, in the order of gamma to the power of T. Right? So this is the same convergence result that we had. So the same convergence rate that we had for policy evaluation. All right. So any questions so far for this, for both algorithm and the convergence analysis?
Quick question.
Yes.
Even if we had, say, infinite time to iterate, because of floating point arithmetic and round off error, and in an actual execution, are we still guaranteed to converge, or is there a possibility because of error and precision that we might not actually converge and might bounce around?
Yeah. So very good question. So I was not planning to talk about this until the next lecture, but yes, you're right. So for value iteration, we cannot actually guarantee to converge, right? Because you could, especially from the policy perspective, which we will talk about in the next slide. So in order for value iteration to converge to the optimal policy pi star, right? So you need sort of some sort of gap between the optimal policy and maybe the second optimal policy. Right? So imagine that you have a situation where the second optimal policy's Q function is very close to the first optimal policy's Q function. So this value iteration needs to run sort of arbitrary many iteration in order to sort of make sure that the error between Qt and Q star are less than that gap. And at that stage, you can separate from the first optimal policy to the second best policy, right? But their gap could be arbitrarily small, which means that value iteration could take infinite arbitrarily many iterations in order to distinguish the best policy and the second best policy.
That makes sense. Thanks.
All right, but the next lecture, we're going to talk about an algorithm that actually guarantees to hit an optimal policy with finite number of iterations. Okay. And in the homework 1, you will actually investigate why the algorithm that we're going to talk about next Tuesday actually hit an optimal policy with finite number of iterations. Yeah, but this algorithm is an approximation algorithm, right? From an approximation algorithm perspective, we are happy about some near optimal solution, right? So the worst case that I mentioned, where the first optimal policy and the second best optimal policy are arbitrarily close, from an approximation algorithm perspective, outputting the first one and the second one, there's not really that much difference, right? I'm pretty happy about outputting the second best one if that's arbitrarily close to the first one, right? But if you really care about hitting the optimal policy, yeah, so this algorithm is not gonna do the job for you, right? Which we will talk about the algorithm actually that does the job in next Tuesday. All right, so far we only talked about the how the Q estimator that we are computing every iteration converge to Q star, right? But recall the goal for today, right? We were actually interested in terms of outputting a policy pi that perhaps is doing as good as pi star, right? Like so far we talked about how to compute Qt, right? How to iterate on Qt so that Qt eventually converges to Q star. But we haven't really talked about how this process actually gives me a policy that I can actually use in the execution time, right? Like a policy that I can use maybe playing this video game or playing this board game. So the next, we're going to talk about how we can actually extract a policy from this value iteration process. Right, so the intuition is very simple, right? So we know that if I had access to Q star, then if I can just act greedily with respect to Q star, right? I can just set the optimal policy to be the argmax operator with respect to this Q star. Right, so this is one of the quantity that we proved on maybe the second lecture, right? So now the value iteration ensures that Qt could be arbitrarily close to Q star, right? So the naive solution that we could try is perhaps just set the policy pi to be the greedy operator with respect to Qt, right? So now we convinced ourselves that Qt could be arbitrarily close to Q star if I set t to be big enough. So maybe eventually, I can just pick the argmax operator with respect to my estimated Qt. And my hope is that when t goes to infinite, pi t is sort of similar to pi star, right? So that's our hope. Right. So I saw there are some questions on the chat window. If you don't mind, you could actually unmute yourself and ask questions now. Okay, I'm actually not be able to simultaneously monitor the chat window at the same time. All right, so we sort of guessed what the policy that we should output, right? So at iteration t, we have Qt available. And what we sort of guessed is that let's just pretend this Qt to be Q star and outputs the policy that corresponds to the argmax operator with respect to this Qt, right? So the hope is that, Qt gradually converges to Q star. So my hope is that pi t, maybe converge to pi star in some sense, right? We haven't talked about, converge in what metric, what distance metric, but hopefully, pi t somehow is very close to pi star. So that was our hope. And this theorem actually sort of confirms our educated guess, right, from the previous slide. So this theorem basically says that if I use the argmax operator with respect to the estimator Qt as my policy, right? And then I compute the value function of this policy pi t. And let's compare it against v star, right? The value function for the optimal policy. And we see that this theorem tells us that the difference between these two value functions is actually scaling with respect to this quantity, gamma to the power t again. Right? So this means that if t approaches to infinite, I actually find that a policy, pi t, right, is actually bigger than v star s for s. Then this must mean that pi t is an optimal policy. Right? Because by definition, pi star is the policy that dominates everywhere, right? So right? Then with this sandwich inequality, I basically convinced myself that v pi t is equal to v star for every state s. Then, v pi t must be, an optimal policy, right? A policy that dominates every other policy everywhere. All right, in the next 15 minutes, this is what we're gonna trying to prove. So this is perhaps one of the most complicated proof that we're going to see in probably in the first half of the semester, right? So all we care about is computing the difference between the value of our policy pi t, right, and this unknown quantity pi star. So let's try to so I don't want to jump into the equations right now. So let's actually slow down a little bit and try to just sort of draw some pictures and see if we can get some intuitions here, right? Okay, so what we care about is actually the difference between v pi t and v star, right? So if I start from state s, so let's see, this is the trajectory that followed by executing our policy pi t, right? And this is v pi t s. All right. And the second quantity that we're interested is this unknown quantity, right? This V star. So let's imagine that this is the trajectory followed by following the optimal policy, actually. And this is V star S. All right, so we are interested in calculating the difference between these two trajectories, right? But this is actually a not very easy task, because if you look at these two trajectories, like they could be widely different, right? Like every time step, you sort of following two different policies. The first trajectory is following pi t every time step. The second trajectory is following pi star every time step, right? It's not super easy for us to directly compute the difference between these two. So what we're going to do is actually to introduce a middle ground, which could make our life easier. So particularly, I'm going to introduce a middle ground that first follows pi t for one step, and then immediately switch to pi star. Okay, so this is what I'm going to do. I follow pi t for one time step, and then I immediately switch to pi star. Right, so what about this middle ground? So this ground, by definition, is actually q star s pi ts, right? Because the first segment is a segment following, is a segment coming from following policy pi t, and then afterwards I just follow pi star all the way to the end, right? So the second, this middle ground is actually q star s, and action is computed from pi t. Right, so now I have three quantities. One, let's call this 2, this 3, right? So I originally cared about 1 minus 3, but now, as we argued, directly doing 1 minus 3 might be very hard. So I introduced middle ground. So now we can actually do 1 minus 2 plus 2 minus 3, right? So we have two terms, 1 minus 2 and 2 minus 3. Let's try to reason about each term independent, right? So let's see how we can reason about 1 minus 2. Right, so our life becomes a little bit easier because 1 minus 2, if you look at the segment 1 and segment 2, right, they actually share the first segment, right? So they both share this segment because they start from S and they take the same action. They follow the same policy, right? So if I do 1 minus 2, at least the first segment will cancel out, right? And then we get to the situation where we actually gonna compute the difference between this segment and this segment, right? Again, so I'm reasoning about the difference between 1 and 2, and we realize that they follow the first action from policy pi t. So the first segment goes away. Now what I left is actually the difference between these two new segments, right? But at this stage, it should remind you something related to recursion, right? So we started by computing the difference between 1 and 3 from the original state S. Now we introduce this middle ground. Now we move to state S prime. And what we cared is actually the difference between the two segments originated from S prime now, right? So this is very similar to the original situation we faced at state S, right? So this suggests us that we can actually do recursion here. Because we started from at state S, we were looking at the difference between 1 and 3. Now we moved one step further at S prime, right? And we started caring about the difference between these two new segments originated from S prime, right? So this is put us back to the situation that looks almost the same as the situation we faced at the original state S. All right, so this is what we're gonna do to deal with the term 1 minus 2, right? In terms of 2 minus 3, it's also a nice quantity because now this 2 and 3, they only differ in the first time step, right? And afterwards, they're following the same policy. Right, so by this middle ground, we put us into a nicer condition in a sense that we can actually care about two terms, 1 minus 2 and 2 minus 3, right? For 1 minus 2, we see some hope to use recursion. And for 2 minus 3, we also see some hope because they only differ at the first point. And afterwards, they at least they are following the same policy, right? So we may only need to argue about difference, raising the difference resulting from the disagreement in the first time step. Maybe afterwards, we can actually, because they are following the same policy, maybe we can deal with that easily. So that's the basic high-level idea. Right? Right, so that's actually what we're going to do for the proof, right? So we're exactly going to introduce a middle ground and then reason two terms. One term is dealt with recursion. One term is dealt by using the value iteration property, the convergence property. Right, so the first step is just writing out things by definition, right? So I'm just writing v pi using q and writing v star using q star. Right, so I'm taking action by pi t, and here I'm taking action by pi star, right? So by definition, this is an equality. Okay, so the second step is exactly the step where I introduce this middle ground, right? So I minus a term, and I immediately plus this term back, right? So this is like 1 minus 3. Did I use 1, 3, 2? Sorry, just give me 1 second. Okay, yeah. So this is 2. This is 2 minus 3, right? This is exactly what we did. So if you look at the term, the term 2, right? The term that we subtract and the plus, right? So this term is actually the middle ground, right? So this term says that I take action by following pi t for one step, and then I immediately switch back to pi star, right? So this is the definition of q star s and pi t s. Right, so now as we sort of reasoned from the previous slides, right? So if I look at the difference between these two quantities, they are nice in a sense that these two quantities share the same segment, right? The segment that corresponds to state S and action pi t S. So which means I can actually cancel the reward for that segment, and I can move on to the next time step. Right, so that's all what we did in this equation. So here, just write out one more step detail. We can cancel reward rs pi ts, right? And then move on to the next time step. All right, so now we get into a situation where we can actually care about the difference between v pi t and v star at the next time step, right? So that puts us into a situation where we can repeat the same process, right? Because we started from caring about the difference between v pi t and v star at state S. So now we get into the next state, and we are computing the difference between v pi t and v star at the next state, right? So this means that we can apply recursion. Okay, but let's hold on recursion for a second. Let's try to deal with the second term, right? The term that corresponded to 2 minus 3 from the previous slides. Right, so just switch color. So now we actually are interested about this quantity, right? Q star at S pi ts minus Q star at S pi star S, right? So let's draw this picture again. So at S, I first follow pi t, and then I follow pi star, right? And comparing to the process of following pi star directly at S. So we care about the difference between these two segments, two trajectories, right? Okay, so what we can do is actually introduce an additional term, which is minus qt measured at S pi ts plus qt measured at S and pi star S. Okay, so let's slow down a little bit here. This step is a little bit tricky, right? As you can see here, the inequality we already changed from equality to an inequality, right? So basically what I'm arguing is that by minusing this term and plus a very similar term back, we actually changed from this equality from the previous time step to the current inequality. Right, so what I'm saying here is this quantity is actually less than 0. Okay, so anyone want to give an explanation why this inequality is true? Yeah, I saw a hand raised.
So the reason is that following pi t is like the optimal solution. So if we change the initial step to pi star, is definitely not following the optimal rewards. So it's like we will kind of reduce the value.
Yeah, so I think you are kind of right. But remember here, we are reasoning about pi qt, right? Qt is some estimator that is computed from the value iteration. Right, so we have to use the definition of pi t. So now it's a good time to recall the definition of pi t, right? So pi t is actually a greedy policy, right? That picks the action that achieves the maximum Q value at this state S. Actually, sorry, my bad. This is inequality, right? So this literally means that by definition of pi t, right? So this basically means that qt s pi t s must be bigger than qt of s or pi star s, right? Because pi t looks at the value of qt and picks the action that achieves the maximum value of qt, right? So that must be bigger than the value of qt measured at another action that is computed from pi star. Right, so this is just by definition of pi t, right? My pi t, always look for the action that achieves the maximum with respect to qt, right? So that's all the inequality that I'm using, and that's why I get the inequality, in this very long expression. All right, so now we get into a very good situation, right? We know the difference between q star and qt. That's the guarantee that we computed from value iteration, right? So erase these things. So now we get into a pretty good situation, right? Look at these two terms, right? This is the difference between q star and qt measured at the same state action pair, s and pi ts. That's nice because we know that the difference between q star and qt are bounded, right, by value iteration convergence argument. So now look at the second term, right? So this is the difference between qt and q star again, and again measured at the same state action pair, right? S and pi star s. That's also nice because we know how to bound it, right? Value iteration convergence tells us that, qt and q star are very close to each other at every state action pair. So now the last step is just plugging the guarantee that we had from value iteration, right? So remember that we had q star minus qt infinite is less than gamma to the t q0 minus q star, right? So here the term 2 is coming from the fact that I'm applying this value iteration guarantee for both terms. So that's why I get a term 2, right? And the gamma to the t times the difference between q0 and q star is essentially the guarantee that we had from value iteration. All right, so that's pretty much the end of this proof, right? And the rest is actually repeat this same process for vt minus v star at the next state s prime. So just repeat, right? So let me just try to, definitely, trying to sort of do one more step, right, to get a sense of this recursion. So let me just write out, one more step. What would happen if you do recursion again, right? So this is like VTS minus V star S is bigger than negative 2 gamma T Q0 minus Q star infinite minus 2 gamma times gamma T Q0 Q star minus so on and so forth, right? And if you combine these terms together, you will basically prove the theorem that we had. Right. So yeah, so I think these detailed inequalities, again, these are details, right? These are like technical details. But I think it would be nice, to try to understand the high level picture that we did from the previous slides, right? And once you set up the goal, bounding the difference between term 1 and 2, and then bounding the difference between term 2 and 3, once we set up these goals that we want to chase inside the proof, then we can actually gradually figure out, the detailed steps to achieve these goals, right? And again, at this moment, you probably have seen this recursion, the idea of recursion, many, many times, right? Like all the proofs that we did in these lectures, we never really complete the entire proof, right? We always start from something that we care about, and we do one step forward. We get to some quantity that looks very similar to the original quantity that we had, and then we can repeat the recursion, right? And the recursion allows us to do infinite many steps, so we get something like gamma to the power of t, right? T is corresponding to the number of steps of recursion you do in the proof. All right, so let's just do a quick summary for value iteration, right? So the big picture is that we started from this fixed point iteration again, right? We realize that Q star satisfies some fixed point equation, and then we just designed this algorithm, right? This fixed point iteration algorithm, and we proved that this thing is a contraction again, right? So this is a usual proof framework. We proved that this operator is a contraction. That immediately gives us this very nice convergence, exponential fast convergence theorem, right? And then we said, value iteration is computing Qt. So let's just try to compute a policy, right? Let's pretend Qt is equal to Q star, and let's just use the argmax operator with respect to Qt as our policy. And then together with the convergence guarantee that we had from value iteration convergence analysis, we proved this policy's performance, right? In other words, V pi t is actually very close to V star, up to the term that scales exponentially with respect to this discount factor gamma, right? And again, this approach to 0 if t approach to infinite, right? So which means that if I do this algorithm infinite many iterations, I guarantee to find an optimal policy. But from an approximation algorithm perspective, after I do maybe 100 iterations, my pi t is already very close to pi star in terms of comparing their values, right? So maybe I'm happy already because all I want is an approximation solution, right? So summary. Let me just quickly summarize what we did for this whole week. We have this whole big main theme for this week, right? So we covered the Bellman equation and Bellman optimality from the first week, right? These are the two properties of the Markov decision process. And from these two properties, we realized that there are two very nice fixed point equations, right? One for V pi, one for Q star. And then we introduced this fixed point iteration framework, right? So this is probably something that you saw from some numerical analysis class. And then combine these properties and the algorithm framework together, we arrive at two algorithms that looks almost identical, right? We just repeatedly apply this fixed point equation on our previous estimator over and over again, right? And then for analysis, we also did the same thing. We just proved that this Bellman equation, this thing is a contraction map, right? And we did the same thing for the Bellman optimality. We just proved that this operator T is again a contraction map, right? And then combine these two combine the general analysis framework of fixed point iteration and the contraction together, we very naturally arrive at these two convergence theorem, right? They looks almost the same. The difference shrinks in the order of gamma to the power of t, where t is the number of iterations, right? And then today we did one more step, a very complicated step actually. So we're trying to get a policy out from this value iteration process, right? Because it's value iteration. The reason that it's called value iteration because it's focusing on computing some values that is very close to the value of Q star, right? So we milk out a policy pi from the estimator Qt, and we reasoned about the performance of V pi t versus V star. All right, so that's basically what we did for this whole week. And for next week, we're going to talk about one more algorithm for computing pi star. Okay, so that algorithm, as I promised you, that algorithm will actually output pi star. It will actually output an optimal policy with finite number of iterations. Okay, and then we're going to switch to a different topic on continuous control. So on next Thursday, we will actually introduce a new model called linear quadratic regulator. So we're going to start talking about some basics of optimal control.